This is my Precalculus course. Today we're going to learn rational functions and how to graph these functions. If you haven't done the homework completely incorrectly from the last class, do that homework before watching this video. A rational function is a fraction, at least it looks like a fraction, and the numerator of the fraction is a polynomial and the denominator of the fraction is also a polynomial. So we have an example here, f of x, and an example here, g of x, and an example here, h of x. Now notice that with this function here, we have a constant in the numerator. And in that case, that polynomial would be considered a 0-degree polynomial, because we can write -2 as -2x to the 0 power. Now, you might recall we learned the reciprocal function in my intermediate algebra course. That's a parent function, and that's the simplest form of a rational function. Now, we need to learn what it means for a rational function to be in lowest terms. That's when the numerator and denominator of a rational function have no common factors. So here's some expressions that you can consider to be rational functions, even though we haven't named these as functions. And if you factor the denominator, you see that we have a factor that is common to a factor in the numerator. And these can cancel out, and we get an expression that we say is in lowest terms. Now, to be honest with you, this expression is not the same as this expression. They're not the same function, but we can use this expression in lowest terms to analyze the graph of the function. But we always have to go back and consider this information here because that affects the graph. We're going to find out what that means later on. So here's another example. We can factor out x in the numerator and the denominator, and they cancel out, and we have the expression in lowest terms. So that's what it means for a rational function to be in lowest terms. We cancel out the common factors. Now, it's important to understand that in order to graph a rational function, we need it to be in what we call proper form. Now, proper form is when the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. Now, all the problems that we're going to do today are problems that involve rational functions in proper form. We're not going to do any problems where we have rational functions in improper form today, but in the next class we're going to deal with those. Now, here are some examples of expressions you might see in rational functions where we have proper form. The degree of the numerator here is 1, and the degree of the denominator is 2. So the degree in the numerator is less than the degree of in the denominator. And here the degree of the numerator is 0, and here the degree is 4. So the degree in the numerator is less than the degree in the denominator, and so on and so forth. So these are all expressions that you might see in a rational function where we have proper form. Now, improper form is obviously the opposite situation, where the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator. So here our degree is 7, in the denominator our degree is 5. So that's pretty obvious, that's improper form. But just be aware that when the degrees are the same, that's also improper form. So if the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator, that is also improper. So make a mental note of that. So we're going to be going over this information a lot later on. But this is a very important three-part theorem. This first part tells us that if there's some x value that makes the denominator 0, then that x value is the location of a vertical asymptote. But that's only true if the fraction is in lowest terms, or the rational function is in lowest terms. So you have to be careful. If the fraction is not in lowest terms, then an x value that makes the denominator 0 might actually be a whole. Okay, it's not going to be a vertical asymptote. A vertical asymptote is an invisible line that the graph approaches. So let's say you have a graph that approaches that pink dotted line like that. That's a vertical asymptote, that pink dotted line. But in the situation where our function is not in lowest terms, you might actually get a whole. So again, we'll go over that later on. Now, if a rational function is in proper form, then there is a horizontal asymptote on the x-axis. And if a rational function is in improper form, then there could be a horizontal asymptote, or an oblique asymptote, which is a slanted line. And I actually refer to curved asymptotes. That's when the graph of a function approaches some curved, invisible function, and that's not really formal, but I'll refer to that. I'll refer to curved asymptotes in the next class. Okay, so wholes appear when you have a factor in the numerator and the denominator that are the same. So again, this is a function that is not in lowest terms because you have a common factor. So these green factors can disappear and you're left with this function. But when the green factors are there, it tells us that we have a whole, because if you plug in 1, you get 0 divided by 0. And so the only purpose of these green factors, the only reason for us to keep them there, is to tell us that there's a whole there. So we're going to go over that later on. If you're a little confused about these things, if you're not really quite sure what we're talking about, that's okay. We're going to learn this as we continue. So I want you to get a picture of all this information here. And I also want you to get a picture of these steps here. These are the steps we're going to follow to graph rational functions. So let's get started. It says here, graph the following functions, draw asymptotes as dotted lines, and write their equations. Okay, so step number 1 is to find the asymptotes. Now, notice that this rational function is in proper form, because the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 0, because remember, we can write that as 1x to the 0 power. So we have a degree of 0 and a degree of 2. So again, because the degree of the numerator is less than the degree of the denominator, the function is in proper form. So our theorem here tells us that because the rational function is in proper form, there's a horizontal asymptote on the x-axis. Okay. So I'm going to go ahead and draw that. So again, that's an invisible line that the graph approaches. And let's write the equation of that horizontal asymptote. So now let's find the vertical asymptotes. So in order to do this, we go to the first principle here in this theorem. It says if the function is in lowest terms, And we actually do know that the rational function is in lowest terms, because obviously there are no factors in the numerator that are going to cancel out factors in the denominator, because the numerator is about as simplified as it can possibly get. So it says if the rational function is in lowest terms, and if there's some x value we can plug into the denominator that makes it 0, then that x value is the location of a vertical asymptote. So what we're going to do is figure out what makes the denominator of the function 0. In order to do that, we need to factor the denominator. So this is a quadratic expression. What two numbers multiply to -3 and add up to -2? So that's going to be -3 and 1. Okay, so what this tells us is that if we plug in -1 or 3 to this function, we get 0 in the denominator. And so those x values are the locations of vertical asymptotes. So that's very useful information. So I'm going to go ahead and graph those vertical asymptotes, -1 and 3. Okay, and so now we're done drawing the asymptotes. So now we're told to find the x and y intercepts of the graph. So to find the y-intercept, all we have to do is plug in 0 for x. So we have 0 squared minus 2 times 0 minus 3. And we get -1/3. So the y-intercept is 0, -1/3. So I'm going to go ahead and graph that. That'll be about there. And now we're going to find the x-intercept. So the x-intercept is located at an x value that makes the y value 0. So remember, f of x, you can think of that as the y value. We want the y value to be 0. Here we wanted x to be 0. Here we want the y value to be 0. So maybe I'll indicate that. So we're letting x equal 0. Here we're letting the y value be 0. And so we're going to set this expression equal to 0 and solve for x. So let me copy that, bring it down. But you can see that there is no x value that's going to make this expression 0. In order for the expression to be 0, the numerator has to be 0. That's what makes a fraction 0. You can make this fraction undefined by making the denominator 0, but that's not the same thing as making the expression 0. You need the numerator to be 0. That's the only way that it could possibly be 0. So that's impossible. The equation is impossible. So there's no x-intercept. Okay. So now we need to get an idea of where the graph is going to be. Let's do a sign chart. And whenever we do a sign chart, we need to mark the locations of x-intercepts. There are no x-intercepts. And we need to mark the locations of vertical asymptotes. Those characteristics of the graph tell us when the graph is going to be above the axis, x-axis, or you can think of them as places where the graph could possibly change from being above the x-axis to below, or vice versa. So let's mark the locations of the vertical asymptotes, and now we'll check these areas. So let's check 0. Let's plug in 0 and see what the sign is going to be. So we plug in 0, and we actually already did that. We got a negative number, so that means the graph is going to be below the x-axis in that region, this region here. So now let's plug in 4. Let's plug in 4 up here, and it's going to be easier to plug it in here than to plug it in up here. So now remember, we don't really care what the output is going to be. Okay, we don't really care what the actual number is. We just want to know if it's going to be positive or negative. So if we plug in 4, we get a positive number here and a positive number here. Multiply a positive by a positive, you get a positive, and a positive divided by a positive is a positive. So this tells us that the graph of the function is going to be above the x-axis in this region here. Okay, so now let's plug in -2. If we plug in -2, we get a negative times a negative, which is a positive. Then a positive divided by a positive is a positive. So this region is going to be positive. We'll mark that with a positive sign. Okay, so now we're ready to start thinking about actually drawing the graph. Now I'd like to know what it looks like in this region, so I'm going to plug in some values. If you're not quite sure what the graph is going to look like, because we could draw it like this, but that's not really what it looks like. So we need to find some more points. So let's try plugging in 2 up here for x. If we plug in 2, it looks like we get -1/3. So 1, 2, and then down 1/3. So now our graph is going to be a lot more accurate. So there you go. That's pretty accurate. Now let's plug in -2, and we get looks like positive 1/5. So -2, positive 1/5. You probably don't need to really find a point there. We kind of know what the graph is going to do, but it's always good to check. So now let's plug in 1, 2, 3, 4. Let's plug in 4, and we get, looks like 1/5 again. So then we connect the dots. We know that the graph is going to be approaching the asymptotes, most likely, and it turns out that that's what the graph looks like. Now you can find more points just to be absolutely sure that your graph is correct, but in most cases, again, the graph is going to be approaching the asymptote in most of the regions. So there you go. That is the process for graphing a rational function. So let's try another one of these. First, we're going to draw the asymptotes. This is a proper rational function. It's in proper form because the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. Again, the degree of the polynomial in the numerator is 0. So again, principle number 2 of our theorem tells us that if the rational function is in proper form, there must be a horizontal asymptote on the x-axis. So I'm going to go ahead and draw that. And I'm going to write the equation of the horizontal asymptote, even though the problem doesn't, tell us to do that. Okay, so now we're going to find the vertical asymptotes. To do that, we have to change the form of the equation. So what two numbers multiply to 4 and add up to 4? Again, this is a quadratic expression. And if you said 2 and 2, you're correct. So that tells us we have a vertical asymptote at -2. And so I'm going to go ahead and draw that. Okay, so we have our asymptotes drawn. Now I'm going to find the y-intercept. In order to do that, we have to let x equal 0. So f of 0 is equal to -16 over 0 squared plus 4 times 0 plus 4, and we get -4. So our y-intercept is 0, -4. Alright, so I'm going to go ahead and plot that. And the x-intercept, well, just like in the previous problem, there is no x-intercept. There's nothing that, there's no x value that would make the numerator equal to 0. We have to let f of x equal 0. F of x is the y value. Remember, to find the y-intercept, we let x be 0. To find the x-intercept, we let y be 0. F of x, you can consider it to be y. So we're letting that equal 0. But again, that equation is impossible. You can just say none. No x-intercept. Okay, so now let's do a sign chart to get a feel for some of the points on the graph. And again, the x-intercepts and the vertical asymptotes are where the graph could possibly cross the x-axis from above the x-axis to below, or vice versa. We don't have any x-intercepts, so we don't have to worry about that, but we do have vertical asymptotes. So let's figure out if the graph is above or below on this side. So let's plug in, let's start with this side. Let's plug in 0. If you plug in 0, well, we already did that. We got -4. So the graph is going to be negative on that side. And on this side, let's plug in -3. If you plug in -3, we have a negative times a negative, which is a positive, and then a negative divided by a positive is a negative. So it looks like the graph is negative on both sides. Now I'm gonna find some other points over here so my graph is a little more accurate. So I'm gonna try plugging in 4. Actually, I'm gonna plug in 2. So if I plug in 2, it looks like we get -1. So 1, 2, -1. And that's probably good enough to make my graph as accurate as it really needs to be for this class. But let's try plugging in an x value over here. Let's try -4. If you plug in -4, we get -4. So 1, 2, 3, 4, 1, 2, 3, 4. So let's plug in maybe 6. Let's plug in -6, and we get -1. So 1, 2, 3, 4, 5, 6, -1. So that just gives us a better idea of what the graph looks like. So there you go. Now again, you could be more accurate by plotting more points, but I'm not going to make you do that. This is not, the purpose of this is just to get the main idea, not to plot the graph perfectly. Okay, so now it's time for you to try. So again, I'm going to give you one more chance to take a picture of this information and take a picture of these first two problems, and we're going to have you attempt number 3 on your own. So go ahead and attempt number 3, and remember, you want to follow these steps. So start by finding the asymptotes. Now notice that the degree in the numerator is less than the degree in the denominator, so we have a theorem that tells us that there must be a horizontal asymptote on the x-axis. So start by drawing that horizontal asymptote, and then you want to find your vertical asymptotes by factoring the denominator and go from there. So try number 3. When you come back, we'll do it together. Okay, we're back. So again, your graph doesn't have to be perfect. Okay, so if you got that one right, excellent. So now I want you to try number 4. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay. So now we're going to go to some slightly different types of problems. Here we don't have a constant in the numerator. We actually have a degree 1 polynomial because the exponent there of the leading term is 1. So the degree of the polynomial in the numerator is 1. The degree of the polynomial in the denominator is 2. So it's less than in the numerator than in the denominator. Again, this theorem tells us that there must be a horizontal asymptote on the x-axis. So I'm going to go ahead and draw that. Okay, and I'm going to write the equation y equals 0. And now we need to find the vertical asymptotes. In order to do that, we have to factor the denominator. So what two numbers multiply to negative 15 and add up to 2? Well, that's going to be positive 5 and negative 3. So notice that we don't have a common factor in the numerator and the denominator other than 1. If we had x plus 2 down here as well as up here, then we would have a hole on the graph. That would be something different, but we don't have that. So x equals 3 is a vertical asymptote, and x equals negative 5 is a vertical asymptote. So now the y-intercept, we're going to let x equal 0 and find f of 0 is 0 plus 2 over 0 squared plus 2 times 0 minus 15. So I'm just plugging in 0 to the function. And we get negative 2 over 15. So the y-intercept is 0, negative 2 over 15. And to find the x-intercept, we let the y value be 0. Remember, f of x is the same thing as the y value. So we need to solve this equation. When f of x is equal to 0, what would make the fraction 0? Well, it's obvious that the numerator is going to be 0 when x equals -2. Again, in order to make this fraction 0, we need to make the numerator 0. Now, if the numerator and the denominator are 0 at the same time, that does not make the function equal to 0. That makes it undefined. But we know that there's no common factors in the denominator. In fact, we should probably just go ahead and write that expression so we can see and confirm that there's no common factors, because that would be a totally different situation. You have to really be careful about not confusing those two scenarios. So when x equals -2, we have an x-intercept. So the x-intercept occurs at -2, 0. So now let's plot that point. Notice that our x-intercept is actually on the horizontal asymptote. It is possible for a graph to go through a horizontal asymptote, although it's not possible for a graph to go through a vertical asymptote. So now let's plot the y-intercept, somewhere around there. And I forgot to plot the vertical asymptotes. We have an asymptote at -5, and we have an asymptote at 3. Okay, so now let's do a sign chart. We're going to mark our vertical asymptotes, but we're also going to mark our x-intercept. And the problems that we did before, we didn't have an x-intercept, but now we do. So we have -5, and we have -2, and we have somewhere over here we have 3. Doesn't really matter if your spacing is correct on the number line. It doesn't have to be perfect. Something like that. Now again, the reason that we mark those locations where we have x-intercepts and vertical asymptotes is that's potentially where the graph can change from below the x-axis to above, or vice versa. So let's figure out where our graph is below or above the x-axis. I'm going to move these in together a little closer. Again, it doesn't really matter if it's perfect. So let's try plugging in, well, we already plugged in 0. We already plugged in a value that's in this region. We found that it was -2/15, right? So that's, our graph is going to be below the x-axis there. And let's try plugging in 4. If we plug in 4, we get a positive number. So the graph is above the x-axis there. Let's try plugging in -3. If we plug in 3, we get our -3. We get a negative number times a positive number, which is negative. And then up here we would get a negative number, so negative divided by a negative is a positive. So the graph is above the x-axis there. Let's try plugging in -6, and we get a negative times a negative, which is a positive. But up here we would have a negative, so a negative divided by a positive is a negative. So the graph is below the x-axis there. Okay, so that's all the work that we have to do to figure out how to graph this. So let's find some additional points. Let's try plugging in x is equal to 2. Then we get, looks like -4/7. So that would be about about here. And let's try plugging in -4. If you plug in -4, you get looks like you get +2/7. So this kind of gives us an idea of what the graph looks like. Something like that. Now again, your graph doesn't have to be perfect. You can see that my graph isn't exactly perfect, but it's good enough. Now let's plug in x is equal to 4, and we get 6/9, I believe. And that's going to be 2/3. So that's enough to help us graph that part. And let's plug in a value over here, maybe -6, and that gives us 9 in the denominator and -4 in the numerator, so -4/9. So that'll be about there. And so our graph is going to look something like this. So again, the graph is not perfect, but we don't really care if it's perfect. We're just getting the main idea. So there was an example where we had an x-intercept. So we didn't have an x-intercept in the previous problems. So let's try another one of those. So this polynomial, or this rational function, is in proper form because the polynomial in the numerator has a degree that's less than the degree of the polynomial in the denominator. So remember, our theorem tells us that if the rational function is in proper form, we have an asymptote, a horizontal asymptote, on the x-axis, and the equation is y is equal to 0. So now let's find our vertical asymptotes. So it looks like we have a vertical asymptote at x equals -1. So let's draw that. And let's find our y-intercept. That's when x is equal to 0. So I plug in 0 into the function. And it looks like we get -3. So 0, -3 is our y-intercept. So I'm going to plot that. So we have that point. And to find the x-intercept, we let y equal 0. But remember, f of x is the same thing as y. So I'm going to copy down our function, just so you can see how this process works. We want to know what makes that expression 0, and let's just write the denominator in factored form so we can be absolutely sure that we don't have any common factors. So you can see that we don't have any common factors. The only thing that would make this fraction 0 is 3. -1 would not make it 0, it would make it undefined. So if we solve this equation, we get x is equal to x is equal to +3. So we have an x-intercept at 3, 0. So it's right on the horizontal asymptote again. Okay, so now let's plot some more points. Well, first of all, let's do our sine chart. So we have the x-intercept at 3, and we have a horizontal asymptote at -1. Again, when you do your sine chart, the potential places where the graph can change from above the x-axis to below, or below to above, are the vertical asymptotes and the x-intercepts. So let's test this middle region, plug in 0, and we get, of course, -3. We already did that. So the graph of the function is below the x-axis there. Let's plug in 4. If we plug in 4, it looks like we get a positive number. And let's plug in -2. So, by the way, the graph is above the x-axis there. Let's plug in -2. And it looks like we get a negative number. So the graph of the function is below the x-axis again there. Okay, so let's find a few more points. Let's plug in -2 to the function. If we plug in -2, then it looks like we get -5. So 1, 2, 1, 2, 3, 4, 5. That's a very helpful point there. Now let's plug in -4. If we plug in -4, we'll get 9 in the denominator and -7 in the numerator. So -7/9 if I did my math correctly. I'm doing the math kind of quickly. So that would be about here. That gives us another reference point. So that's what our graph looks like. Okay, and let's plug in 1, 2, 3, 4, 5, 6. Let's plug in 6 and see what we get with that. So that would be 3/49. So that's a pretty small number. It's pretty close to the x-axis. Let's try plugging in 1, 2, 3, 4. And we get 1/25. Also a really small number. So it's kind of hard to see exactly what the graph is doing. But it looks something like that. We don't really need to have much more detail. So there you go. There's some more examples. And so I want you to get a picture of these two problems. And I want you to try number 7. So go ahead and try number 7. Remember, start by drawing your vertical asymptotes. Because this rational function is in proper form, the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. Our theorem tells us that there must be a horizontal asymptote on the x-axis. And to find the location of the vertical asymptotes, you have to factor the denominator. So go ahead and try number 7, and when you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. So I want you to try number 8, and when you come back, we'll do it together. Okay, we're back. So that is what the graph looks like. So if you got that right, excellent. So let's double check everything. Make sure it looks right. Everything looks correct. Okay, so now let's try another type of problem. Now, this is the same type of problem that we did in the previous two examples, but we're going to have a hole. So the graph is going to look different, and this factor is going to cancel out. Now, first of all, this is in proper form because the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. The degree in the numerator is 1 and the degree in the denominator is 2. So that means there's a horizontal asymptote on the x-axis. So now first of all, let's write the equation of the horizontal asymptote. And let's factor the denominator to find the locations of the vertical asymptotes. So this is an unusual situation because look what happens. Those factors cancel out. That's different. So we can write a new function, I'm going to call it g of x, that is in what we call lowest terms. Remember, we talked about lowest terms. That's where we defined this phrase here in lowest terms. That's when that's after you cancel out all the common factors in the numerator and the denominator. So now we have this new function, which is not exactly the same as the other function, but it'll help us to graph. And what this indicates is a hole. What makes the green factor 0? -1. So there's going to be a hole on the graph at -1, because if you plug in -1 to this function, you get 0 divided by 0. That doesn't have any meaning. That's undefined. Now if you plug in 5, the function is also undefined, but when the factor doesn't cancel out, you have a vertical asymptote. So we have a vertical asymptote. I guess I'll just write it down here. We have a vertical asymptote at x is equal to 5. So now let's find the y-intercept. That's when x is equal to 0, of course. So we need to find f of 0. That's 0 plus 1 over 0 squared minus 4 times 0 minus 5. So we get -1/5. The y-intercept is 0, -1/5. Let's plot that. And now let's find the x-intercept. So to find the x-intercept, we let y be 0 and solve the equation. And so we need to let this expression equal 0. And the question is, are there any x values that make this fraction 0? Now you would think that plugging in -1 would make it 0, but the problem is we have, again, a repeating factor. So it doesn't make it 0, it makes it 0 divided by 0, which is not the same thing as making the fraction 0. that makes the fraction undefined. So what you have to do is you have to cancel these factors out and then ask yourself, is there any x value that makes this expression 0? And the answer is no. So let's see if we can find some more room here. I guess we can use an arrow. Remember, whenever you run out of room, just use an arrow. So we can say none. There is no x-intercept. Okay, so let's do our sign chart. We only have one location where the graph can possibly change from above the x-axis to below, or vice versa. We don't have an x value or an x-intercept, but we do have a vertical asymptote at x equals 5. So I'm going to draw that. And so now we need to find some reference points. We know that there's a hole at -1, but really what we're doing is we're graphing this expression here. The x plus 1 doesn't affect anything. It doesn't affect the graph anywhere except at x equals -1. So let's just graph this expression. That expression is going to look something like, let's do the sign chart. So let's plug in 0 and we get a negative number. Let's plug in 6 and we get a positive number. So we know the graph is going to be below the x-axis to the left of that vertical asymptote. And we can plug in some other reference points. So let's plug in 4 and we get -1. And that's probably all we need. And let's plug in 6 and we get 1. And there you go, that's what the graph looks like. But we haven't considered the hole. The hole occurs at -1. So let's go out -1 and let's change this to a hole. That has to be a hole. If it's not an open dot there, then our graph is not correct. So you see that? When you plug in -1 to the function, you have 0 divided by 0. Because that green factor makes it 0 divided by 0. When you plug in -1 here, to the original expression, you get 0 divided by 0. That's what that green factor tells us. So the function cannot be defined there. You have to have an open dot. Okay, so let's try another problem like that. And by the way, you can find the location of the hole, the actual coordinates, by using this function here. So we want to find g of -1. And we get -1/6. So the actual location of that hole is -1, -1/6. You don't really have to do this if you don't want to, but it's probably a good idea. Just so you know you're drawing the hole in the right location. You can see that we did do that. Okay, so let's try number 10. So the fraction is in proper form. So our theorem tells us that there is a horizontal asymptote on the x-axis. And now we have to factor the denominator to, well, actually we're going to factor the numerator and the denominator. We can factor out 3 in the numerator. And the denominator is a quadratic, so we're going to factor that. And so again, we have factors that are common to the numerator and the denominator. And so if we define a new function here and call it 3 over x plus 2, this will help us to graph the function, and it'll help us to find the exact location of the hole. But we know there's a hole at x equals 5 because that makes the expression 0 divided by 0. And maybe I'll color code that over here too. Okay, so we also know we have a vertical asymptote at x equals -2. So we got that there, and I'll color code that on that problem also. So let's draw the vertical asymptote. So now we need to find the y-intercept. So that's when x is equal to 0, so we're going to find f of 0. So 3 times 0 minus 5 over 0 squared. Actually, is it 3 times 0 minus 15 over 0 squared minus 3 times 0 minus 10. So we have 3 over 2, it looks like. So the y-intercept is 0, 3 over 2. So I'm going to mark that. And looks like I already found that the x-intercept, well, it doesn't exist, because there is no x value that will make this expression equal to 0. There is an x value that will make it undefined. There's an x value that will make it 0 divided by 0, but that's not the same thing as making it equal to 0. Undefined and 0 are not the same thing. So we want to set the y value of the function equal to 0. So we want to find what x value makes it equal to 0. And we don't really have a lot of room here. But this reduces to, let's write the factored form. We found up there that it reduces. Let's move this up. And so you can see here, there's no x value that makes this expression 0 once we cancel out the common factor. Again, we can't plug in 5 because that'll just make the expression 0 divided by 0. That's not the same thing as an x-intercept. Okay, so now let's do our sign chart. We don't have an x-intercept, so we'll just mark the location of the vertical asymptote. And we already figured out what the sign would be if x is 0, that's positive. And if x is -3, for example, then we have a negative number. And we can plug in points. Now again, you want to use this expression to graph. And if you want to find the actual coordinate of the whole, we can go ahead and do that. So again, you want to plug in 5 to this expression. So g of 5 is equal to 3 over 5 plus 2, which is 3 over 7. So 5 comma 3 over 7, that's the location of the whole. But again, it's not really useful information until we use this expression to graph. So if we plug in, let's plug in -1, then we get 3. Let's plug in 1, and we get 1. And that gives us pretty much everything we need to graph on this side of the vertical asymptote. Now let's plug in -3, and we get -3, it looks like. And let's plug in -5, and we get -1. And that gives us everything we need to graph. So we can't forget to draw our hole. We have a hole at x equals 5, and specifically it's 5 3/7, 5 comma 3/7. So that would be somewhere around here. So I'm going to draw a hole there, and then we know that our graph is undefined there. Okay. So go ahead and get a picture of all this information. And I want you to try number 11. And so we have proper form. The rational function's in proper form, so that means there's going to be a horizontal asymptote on the x-axis. And then you need to factor the denominator and use the factor that cancels out to help you find where the hole is. And the factor that doesn't cancel out, that's going to tell you where the vertical asymptote is. So try number 11. When you come back, we'll do it together. Okay, we're back. So there you go. So if you got that one right, excellent. Okay, so I want you to try one more of these problems. Go ahead and attempt number 12. You can use number 11 to help you. And when you come back, we'll do it together. Okay, we're back. So there you go. If you got that answer, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, screenshot number 2, and screenshot number 3, 4, 5, 6, and 7. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1, and number 2, and number 3. But don't go before you get the answers. Remember, it's not enough to attempt the homework, it must be done correctly. So here is screenshot number 1 of the answers. and screenshot number 2, and screenshot number 3. So get that homework done completely, correctly, and neatly, and I'll look forward to seeing you in the next class.